Okay, so it looks like my recording kind of stopped at the end there, but what I was saying was that this natural log 11 equals 2x is an appropriate way to rewrite e to the 2x power equals 11, because again, with this base of e, it's implied to be e here, with this base of e raised to the power of 2x, that must equal 11, and that's exactly what we have written in the step before. So the last thing in order to solve for x is to simply divide both sides by 2, and we would have the natural log of 11 divided by 2, and that's x. Now, I wrote this note up here because this is a solution that we can obtain without a calculator. In fact, if I ask this question on a no calculator portion of the test, I would expect to see this as a solution. But since this is calc permitted, further instructions might ask us to provide an answer accurate to 4 decimal places, and we could do that. So I'll switch to the calculator, and I know that a fraction is necessary, so I'll press Control Divide first, then I'll press Control and then this e to the x power key, because that calls the natural log command, and now we can evaluate the natural log of 11 and divide that by 2. Now I know I want a decimal answer, so I'm going to have to press Control and then Enter. If I had just pressed Enter, then chances are the calculator wouldn't do much. These calculators, especially the ones on the computers, like to give precise answers if they can, and natural log of 11 divided by 2 is more precise, so that's the answer it prefers. We've got to force it to provide the decimals, and so we'll go with 1.1989 as this final answer. And again, I like 4 decimal places when we use the calculator. Here's another example. We could add 1 and then divide by 2 to isolate the logarithm. That way we'd have log of 8x equals 2. After we add 1 and then divide by 2, we're left with 2. Now the use of parentheses here is pretty common, although it's also common not to include them. There's kind of this implied grouping symbol around there. So if I happen to forget mine, that's quite all right. Now, one thing I do want to point out is that with this logarithm written and no base indicated, we can assume that the base was 10. And if the base was 10 here, then using that loop rule to rewrite logarithms, we could say that 10 to the second power is equal to 8x, which of course means that 100 is equal to 8x, and x would be 100 divided by 8. When simplified, we would have 25 divided by 2. And again, this whole question was completed without a calculator up till this point, and even with that, we can probably figure out that 12.5 is the next solution, and that could be done without a calculator as well. So those are pretty good indicators of types of problems that we can do with a calculator and without a calculator. And the next two word problems are ones that we haven't covered in the videos just yet, but if you've already started your Math Excel assignments, you've likely seen these. So let's start with this half-life of radium problem. The general format for an exponential function is y equals c times a to the x power, where y is an end result or the output, and c we call an initial value, a we call the base or growth factor, and x is our input or our unit of time many times. And even though we might not end up using logarithms to solve this particular problem, our understanding of exponential equations is going to be very important. Right off the bat, we're told that the half-life of the element radium is 1,690 years. And we don't know the growth factor, or in this case, the decay factor. We don't know the A value associated with that. What we do know is that whatever C value we started with, whatever initial value we had, there's going to be half of that left after a time of 1,690 years. So whether we start with 100 grams or 1,000 grams or 1,000,000 grams, half of that will be left after 1,690 years. It does not matter what our C value is. In fact, when I divide both sides by C in order to isolate the A, the growth factor here, you'll notice that C ends up canceling on both sides. We're now left with 1/2 equals A to the 1,690th power. And that may seem strange at first, but in reality, the solution to this is quite straightforward. Since the variable is the base and not the exponent, we can use a radical to isolate this A value. And the radical happens to have an index of 1,690. So that'd be strange to say that out loud, but that's exactly what's happening. We are solving for A, and A happens to be the 1,690th root of 1/2. Or in other words, A is the number that multiplies by itself 1,690 times to equal 1/2. Now, if I go to the calculator and try to obtain that decimal, it's likely to give me a decimal value that requires much more precision than my calculator can handle. So it's just not worth it. I'm going to leave A in this format. I'm going to leave A alone and not round it whatsoever. Now that we have A, our growth factor, or in this case the decay factor, since the radium is decaying with time, we can actually attack the second half of the question. There are 60 grams of radium that are present now, and how much will be there in 400 years? Well, what we're looking for is an ending amount, Y. If we start it with 60 grams, we're growing at a rate of 1,690th root of 1/2. We're going to let this thing run for 400 years. We're going to let it decay for 400 years. So if we started with 60 grams, we'd like to know how much we're left with after 400 years. So by switching to our calculator now, we can pretty easily compute that. We know that Y is equal to 60 times the 1690th root. Now, if I press the second key, or I'm sorry, the control key and then x squared, that's going to give me just a square root. What we want is the nth root where we can specify the index. So I'll press control and this button. And we'll enter 1,690 as our index. We'll enter 1/2 as our radicand. And then we'll jump to the outside of that grouping symbol and we'll raise that to the power of 400. Now if I just tap enter, I'll get an answer that doesn't really mean a whole lot to me. If I press control enter, it will repeat the calculation this time with the decimal result that is perhaps more meaningful. So I'm going to go with 50.9215. Y equals 50.9215. And we're talking about grams. After 400 years, only 50.9215 grams will be present. Now for our last example. A pretty straightforward exponential growth or decay formula would most likely be fine here. Y is equal to C times A to the X power. We don't know the initial value and we don't know the growth factor here because all that we're told is that this hay was contaminated by a radioactive isotope of some element or some material, and that material has a half-life of 5 days. We know that it's safe to feed the hay when to the cows when the isotope reduces to 12% concentration. And so our question is, how long will it take? We're going to actually have to solve for t this time, or x in this case, because x is our independent variable. In this type of problem, I like to use whole numbers to represent percentages, and we know that the half-life means that 50% of that material remains, and initially we started with 100%. We don't know the rate at which it decays, but we do know that it takes 5 days in order for that to happen. And so by dividing by 100, we get 1/2, and that equals A to the 5th power. By the way, that's a shortcut if you recognize that pattern there. Half-life, 5 days. So A would be equal to the 5th root of 1/2. That's our growth factor, or decay factor in this case, for this particular isotope. So we know that the hay is safe to eat when the amount of material left is 12%. When we started with 100% that had a growth rate or decay rate of the fifth root of 1/2, we can now use our algebra skills to solve for x. So I'm going to divide both sides by 100, and I'll have 12 over 100, which could be reduced. And we have the fifth root of 1/2 that's being raised to the power of x. Now here's where logarithms really come into play, why they're so important for us. Since x is the unknown value in the exponent here, there's no real easy way to undo that. I can't take the xth root of something to isolate the variable x. So instead, I think it would be nice, or at least a little bit easier, to deal with a logarithm, something that we can enter into the calculator, that would replace this exponential function. So I'll recall that the definition states that the base of the exponent becomes the base of the logarithm. So I'll use a logarithm with a base of the fifth root of 1/2. The input, the variable of our exponential, becomes the output of our logarithm, and the output of our exponential, what was the result of our exponential, becomes the input of our log. Now 12 over 100 could be reduced to 6 over 50 or 3 over 25. I'm just going to change it to a decimal because I know I'm going to a calculator here in a second anyway, and 12 divided by 100 is 0.12. So evidently x, the amount of time that needs to pass, is simply equal to the result of this computation. Now without a calculator this would be a good answer, but since we do have a calculator we can see what the decimal equivalent is. And we'll call the logarithm command, which is this key here with the control button. Control then that key. The base of the logarithm is the fifth root of 1/2. And the argument of the logarithm is 0.12 or 12 over 100. However you want it to report it, as long as it's equivalent is okay. Pressing enter sometimes doesn't work. It doesn't give us a decimal, but I think since I wrote this equation or expression with a decimal, then an answer with a decimal was also prepared. So I'm going to call this 15.2945. 15.2945. And our unit for x was days. So evidently, based on the radioactive material that was released in the atmosphere, when it only has a half-life of 5 days, it would be safe to feed hay to the cows after the farmer waits a little over 15 days. So I hope these examples help. If you need more examples or you want more practice, make sure you log into Math Excel, go through the study plan. If you go through the study plan for additional practice, you can find Chapter 6, Section 8, and there will be many more examples for you to practice, as well as help tools that you can utilize from there to make yourself better. Thanks for watching.